Hello everyone, my name is Marco Antonio Sotelo. I am a senior specialist in the Digital Labs division at Indra company in Spain, and today we're going to present a work entitled Adaptive Mitigation of Tactical Denial of Sustainability. The work has been done with my colleagues Jorge, Maestre, and Roumen Daton, they from Indra company as well. In today's presentation, I will go through the following topics. I will start with a short introduction, then I will briefly recap the concept of tactical clouds. I will present or stress the most important highlights of this research work, along with a review of the economical denial of sustainability, or EDOS, and the tactical denial of sustainability, or TOS concepts. Then I will introduce the hybrid architecture that we are considering in this proposal, and then I will come up with an adaptive defensive model for mitigation of TOS threats. We are considering two types of TOS threats here, which I explain further in the following sessions. So let's start with the introduction. In the last years, we are witnessing a growing digitalization of the defense sector. It embraces several areas of applications such as connectivity, data management, data analytics, smart and enhanced cyber capabilities, and several other ones. All of them with the goal to attain technological sovereignty, which is expected in the next decade conflict. But the situation is also pushed by emerging trends or emerging technologies such as 5G and beyond. In terms of network communications, we have a bunch of virtualization technologies. We have cloud and edge computing massively adopted. We also see a deep immersion of artificial intelligence, and we are in a rate of quantum computing nowadays. And all of these technologies are already in place, providing solutions to boost the forthcoming combat capabilities in terms of fusion, network-centric, or information warfare. And a task they have in common is that they should enhance the federated networks in terms of connectivity, latency, and data management for, importantly, end-to-end military communication, being this as one topic of interest for this research. We should also stress the concept of tactical clouds, as they recognize the need to deploy critical communications at the tactical edge of military operations. What tactical clouds are characterized for is receiving different mobility rates, heterogeneous waveforms, the existence or coexistence of different routing policies, and, more importantly, the scalability of the computational resources at the edge. In general, common edge applications include image recognition, natural language processing, situational awareness, among several others, and what they have in common is that they reduce the latency and the response time for the user to the service node, but instead they assume a higher processing overhead. With in mind that the tactical cloud pursuit is the fast and adaptive distribution of the computational node along the operational environment, but this goal entails challenges such as the compliance of cross-domain policies, the awareness of reachability or bandwidth limitations, especially those geographically constrained. It entails also security issues and, importantly for this research, the sustainability and energy efficiency concerns. So in this picture, we are considering two dimensions, two risk dimensions. One related to the information and communication technologies in the left-hand side, and the other related to tactical or operational risks. Both we have stressing a fact and raising a research question. In the first one, we assume that the ICT infrastructure is scaled. So what we question here is what happened behind such scaling decisions. Do we usually cross-check them, for example? On the other hand, we recognize that as processing increases, so is energy consumption. So what we question here is what impact does it have in the overall tactical, operational, or even strategical goals? We will also see that this comparison will help us to shape the scope of EDOS and TDoS threat later in this talk. So these are the main highlights of this research. Previously, we have coined the concept of tactical denial of sustainability and its relationship with the economical denial of sustainability, or EDOS, and presented also some cases of study. And the purpose of this research targets the design of an adaptive strategy to mitigate the TDoS threats grounded on two main concepts, which are the self-organized networks, or SON, and the observe, orient, decide, and act loop, also known as the OODA loop. As a reminder, a workload-based economical denial of sustainability attack is characterized by a situation where the attacker sends costly requests to the virtualized service in such a way that it forces its escalation. It means the creation of additional uh, running instances capable to handle the amount of workload already produced. This type of attack doesn't have the intention to collapse the service, but the only intention to increase the number of running instances. On the other hand, we have the instantiation-based EDOS attack, which is characterized by a situation where the attacker sends or exploits the scaling mechanism itself provided by the NFBI platform, for example, in such a way that it increases or raises the number of running instances more and more with no direct relationship with the actual workload produced by the users. It means or it has as a consequence that we can observe different levels of productivity in the running instances. Some of them might be optimal, but many others can be running average or even lazy productivity levels. And with that in mind, we present here the overall TDoS picture. And this is not a situation of obvious attack, unlike denial of service, for example. And here the attacker also pursues performing even slight degradations of the service. For example, reduce latency from 3 to 5 milliseconds. But as stressed before, it relies on deficiencies that might go undetected by a team. For example, scaling decisions not commonly cross-checked once they are configured. And the important aspect here, as shown in the picture on screen, is that they produce a vertical propagation. If we see in the technological level, where we have attacked a sample deployment of virtualized network for network function, even a slight failure or degradation of a service can produce side effects in the tactical level in terms of the network operation or data center, and they can also propagate to the operational level or even to the strategical one. So what is also important to stress here is the scope of the two threats. The EDOS, which spans the technological or probably part of the tactical level, and TDoS, which has a larger area of influence, as it can span from tactical operational or up to the strategic level. Here we present an example of a maintenance-based tactical denial of sustainability, also known as UTDoS, where the commander has the purpose to delay the activities of the digital capability provided by the adversarial tactical cloud in such a way that it permits rearming the anti-aircraft artillery system. For this purpose, the commander triggers workload-based DDoS attacks that will have a desired effect, which means it will produce desired delays in the adversarial capabilities so that the rearming process is possible. Similarly, we have an example of a deployment-based tactical denial of sustainability, also known as DDoS, where the commander has now the purpose to dissipate the adversarial cyber propaganda before it reaches the civilian devices or civilian population devices by exploiting a DDoS attack. In particular, the commander takes advantage of zero-man capabilities of a proxy state so that it will exploit or it will trigger instantiation-based economical denial of sustainability attacks in order to generate decoy networks so that the adversarial can target their activities against them instead of the real devices of the civilian population. So, moving to the next section of this presentation, we introduce here the high-level architecture that we have considered in the elaboration of this work. Starting from the bottom part of the picture in the technological level, what we consider here is a multi-edge deployment. We are aware that each of the edges can have a different number of virtual running instances as well as different services provided. We consider also the existence of local service managers as well as analysis nodes in some cases, a concept that I will explain a bit later in this talk. Moving up to the tactical level, we observe here the concentration of all the tasks related to the management of the infrastructure and the provided capabilities. We have, for example, functions related to data center management, we have network operations, and importantly, we have also here the multi-edge orchestration capabilities. So, in highest level, the operational one, we have higher level objectives such as intelligence, surveillance, and reconnaissance. We have also situational awareness, and we have also command and control objectives that are intrinsically related to the underlying technological capabilities. And here we present an adaptive defensive scheme to address the mitigation of TDoS threats. This scheme is grounded on the OODA loop concept, as stressed before, and is adaptive in the sense that it deploys or calibrates the deployment of defensive countermeasures according to the risk level identified. It means the higher the intensity of the attack is, the higher the processing overhead it will impose the platform. It has direct relationships with each of the stages of the loop, where we have the observe stage that matches the regular monitoring, we have the orient that responds with the lightweight analysis, and in the same way the decision responds to the inspection, whereas act matches with the mitigation phase. It's important to remark here that transiting from a lower to a higher risk level means that two conditions are met. First, that it is continuously, or the platform is continuously observing scaling out requests, as well as some sort of malicious or suspicious activities that I will explain just in the next steps. And to have a better understanding, I will go through each of these stages. First, we have the regular monitoring, where the underlying scaling system, it means the scaling engine that is already building in the NFBI platform, decides or takes decisions on when to scale. It can be based on different set of policies, sometimes fixed, sometimes fixed consumption templates, adaptive thresholds, or so on. But it's completely ruled by the NFBI platform. So the triggering condition to transit to the lightweight analysis stage is detection of scaling out requests. So the lightweight analysis, once activated, starts to differentiate two situations. In the first, when we talk about UTOS attacks, the analysis is focused on virtual functions where a minority of users or groups cause the highest cost in the infrastructure. But in case of the deployment-based TOS or DTDOS, it looks for groups or instances of running instances where the resources are notably underspent. To accomplish this, we have basic clustering methods or simple analytic models such as the Pareto analysis, also known as the 80-20 rule. We see in the bottom part of the screen two examples of this, where the Pareto analysis shows in the blue graph a small number of users representing the highest process overhead, and on the other, in the other picture, we have a classification of the running virtual instances with those red dots in the bottom part exhibiting or showing scarce levels of productivity or performance. In this stage of the analysis, in the lightweight stage, we have also two triggering conditions. If we detect non-suspicious patterns or scaling decisions, we go back to the regular monitoring. But if we detect such suspicious behavior, we trigger attestation-proof methods, which are going to be forwarded to the mitigation stage. And also, if we don't detect any sort of suspicious behavior, but the infrastructure keeps scaling out, it triggers the following stage, which is deep inspection. Arriving at inspection means that we are already in the highest level of risk, as we were not able to differentiate such a group of users that can explain the rising consumption of resources and the associated costs thereof. In consequence, we are seeing a situation where the sustainability of the platform or the operation is compromised. This imposes a high processing overhead as well, and in consequence, the deployment of temporal analysis nodes may also be required. And this stage is particularly challenging because we should provide here advanced fraudulent resource consumption models. That is basically, as shown in the picture below, a situation where we should clearly differentiate patterns of normal or regular use from those cataloged as anomalous. But it's also important to find the boundaries between them. And that's particularly important because that is exactly the area of influence of TDoS. To accomplish this task, we usually rely on time series analysis, advanced time series analysis. We can rely on deep learning models. We should rely on anomaly detectors and so on, with a purpose to have awareness of such boundaries, as I explained. Here we have also two triggering conditions. One, if we are capable to identify fraudulent resource consumption, we should go to the next stage, which is mitigation. But if we are unable to find situations of fraudulent resource consumption, Or if we see scaling requests, which means that the platform is regulating itself, we should go back to the previous analysis stage, which is the lightweight analysis. And finally, we have mitigation. Depending on the path towards mitigation, we can consider several choices here. For example, we can have the disconnection of non-attested users. Remember those that come from the lightweight analysis and were requested to provide an additional level of validation. We could also consider here the commission of edge services or the decommission of the full edge in situations where justified. We can also see here to drop connected users when fraudulent resource consumption patterns are already identified. It means that remember that in these cases those fraudulent users were previously labeled as regular or normal ones. And regardless of the mitigation strategy deployed here, we suggest to run a workload redistribution algorithm or strategy in order to ensure that we are running only the precise number of instances of virtual instances in accordance with real user demands. It means that we look for release such instances that are not really needed, and by doing so, we trigger some scaling decisions or some scaling requests in the platform. It will help us, in consequence, to go back to a lower risk level, which is the lightweight analysis. But in the opposite, if by doing all of the mitigation actions, it's not possible to scale in the platform, it is suggested to go back to the deep inspection method in order to keep trying to performing analysis until the mitigation could succeed in triggering scaling decisions to the platform. And this brings me to the end of this presentation. Thank you for your attention.